Hopefully we can finish discussing on the hashing stuff that we started discussing a few days ago. I think last class I mentioned we briefly discussed on the skip list, right? Skip list. What was a skip list again? 다 들린다. 다 들려. 얘기하는 거 다 들린다. 다 들려. Okay. What was a skip list again? What was the property of a skip list compared to a general list? It has a extra pointers, right? What was the main reason of having those extra pointers? What was it again? Yeah. Hopefully we can achieve a better search time. Well, not just for the search, in terms of addition, inserting or deleting elements. Hopefully the main idea is we don't have to go through all the n elements in the list. Hopefully we can skip few by having a jumping pointers from one point to the others, and hopefully we can achieve a bit better. But in worst time cases, still worst case is still big O of n, right? In the worst case, we have to go through all the elements in the list, right? And then we start discussing, hopefully we can implementing a hash table like dictionary using a skip list and stuff, right? What was the dictionary again? What was the main features of the dictionary that we discussed? 뭐였어? It's a key and value they store in the position. When we try to get the value of something, then we usually give a key so we can find out where those things are located in the list or memory, whatever you feel like to call it. So that was the main idea. So it was somewhat like a database design as well. So, and I think I show you the Python website for the dictionary representations, right? There was some functions were discussed just like any other ADT that we have looked at so far. Insert, deletion, search, but it was a bit more convenient to use because everything is with the key, so it was much faster to do it. So that was pretty much a summary of what we discussed on a few days ago. It wasn't very difficult, right? Except maybe where to put those pointers in the skip list. Maybe it depends on where you put it. It might be an issue on that part. One other point. What was it? Level I, they call it as a level 0, 1, 2, 3. If you're in level 1, you're skipping every other element. Level 2, 2 to the 4 is skipping every 3 elements, and then you go to 4th place right away. Those are levels and number of elements you skip in the list. Also discussed briefly in our slide. Bit more implementation of using pointers and stuff. I pointed at those examples in the textbook. Hopefully you can read it through, those implementation details, as well as the list of ADT operations for this dictionary or skip list, if you wish. Anyone is listening to me or just staring at the wall? Well. Okay, and then we briefly start discussing on the hashing, right? What was the example that I showed you in the screen last time? What did I do? I was doing something not related to the course, but I just wanted to give you the idea of hash keys, right? I used a BitTorrent, and it seems every movie file that I try to download over the BitTorrent have some type of hash key, so we can find out where the movie file is. I know you guys are using a lot of BitTorrent and it's similar tools. You're actually downloading stuff from your so-called peers, not just from multiple peers at the same time. Hopefully hash key is play their role somewhere to find out where your target files are. And the program that you're using, they give you the hash key of those files too, right? So that was another real life example on hash keys and stuff, right? What was the advantages of a hashing key in searching? There was a time complexity of maintaining hash tables. Constant, right? And that's the beauty of hashing. And then we start looking for a very easy hash functions, like using a modular values, modular operations. So this was the case. We start looking at it. So if you have 8 places in your list, your bucket value will be 8, and your key will be modular by the bucket size, and you can find out where to go into this list, each pair that we store. Again, if you want to find the location of certain values, then you get the key and put it to the hash function, you know the location right away. And then we start discussing on what was the problem of this approach. This was ideal case, no problem at all. There is always place for a new elements. 그죠? I feel like I'm speaking continuously without stopping at all. Because I don't get any signs from you guys. Hopefully you guys are listening. So this was a problem, right? It seems I gave the different keys. I put it in the same hash function. It turns out the value that I got is it's the same location value. So and I try to add a new pair into that same location. It seems there's already another pair is in place. So I don't have any other space to store a new pair, right? That was a problem. What was it called? Collision, right? Collisions. So home bucket, the first hash function values that you get, in this case is 25. Key 25 have a same hash key function. After you put 25 in the hash key function, you will get the same value as by applying 33 in the same hash function. So collision situation is collision. Keys that have the same home bucket are called synonyms. 25 and 33 are synonyms with respect to the hash function that is in use. Anybody care to look it up, hash functions on the internet? I mean, type in hash function on the Googles? No? Anybody did it yet? Do it over the weekend. I don't care. Then you will have a list of hash functions that you can simply just copy it from. They probably have a bunch of hash functions in different languages. It's usually a couple of lines. It's not that long. Sometimes it's a bit difficult to understand what they're doing, but it's interesting to take a look at how many hash functions that you can find on the net. I recommend you type it in, and certainly you can find the entire example of using hash tables and hash functions and different hash tables and architectures stuff. So do look it up. There is more things out there than outside the textbook. So 좀 찾아봐. hash function이라고 치면 이렇게 금방 이렇게 카피해서 쓸 수 있는 hash function들이 상당히 많아요. 근데 뭐가 너무 많아서 뭐가 뭔지 잘 몰라. 안에서 뭐라고 했는지 이해하기 좀 어려운 것도 중간중간에 있고. So when collision happening, what was the next problem they try to add? Go wrong. Overflow. Collision is someone is already in my home bucket. Overflow, so the home bucket for a new pair. Okay. So it's obviously when a bucket contains a whole bucket can hold only one pair, collision and overflow occur together. Assuming your hash table can only hold one at a time, then when collision happens, basically overflow can happen. Later cases, if your list can hold more than one pair, then collision happens, overflow may not happen. There might be a number of pairs the single spot can hold. Then collision and overflow may not happen at the same time. That's why it says if there's only one spot, overflow and collision are happening together. Like I mentioned on Monday, there are, if you look into Microsoft vulnerability report website, like CERT. CERT가 뭐지? What was a CERT? If something happens in the internet, if something happens like hackings, and a couple of days ago we had some DDoS cases, whatever those are, and there's a certain website that you can go to. What was wrong with those systems and stuff? Those sites are maintained by sometime by the government, sometime by universities, and if you go into those one of those websites, then the probably most occurring word in those websites is probably something called buffer overflow. Buffer overflow, the same problem. So somewhere in their program, they also using this type of list, and they design it wrong, or they didn't expect something like that happening. So buffer overflow happens. There's no spot to store any elements. So that some people looking for those faults in the program, and hopefully they can hack or they can change something in the program too. So again, you can type on the CERT on the web. 그 마이크로소프트에서 하는 그 윈도우즈 업데이트 같은 거 하잖아. 윈도우즈 업데이트 같은 거 하면 마이크로소프트에서 하는 웹사이트에 들어가면 이 업데이트는 뭐를 고치기 위해서 하는 업데이트입니다. 쭉 설명을 해놓은 게 있어요. 근데 제가 가서 보면 가장 많이 나오는 단어가 버퍼 오버플로우를 고치기 위한 겁니다. 뭐 이런 게 많아. 상당히 그런 게 많습니다. So that is the main problem of some of the programs, and that you're using it at this moment too. So, overall idea is, if something like this happening, overflow happening, what can we do in the basic hash tables? What are the general approaches to solve these situations? I gave you a brief hint yesterday, Monday. What can you do? What might be the dumbest idea of doing this? If you have no place in the list, dumbest approach that you can find. Increase the size of the list. I don't know. Then you increase the number of buckets. Then the value for B is now increased. You're hoping for that there is no more collision after I increase the size of the list, right? That might be the dumbest approach, but it's a similar approach in when we're discussing array list and link array representation of other data types, data structures. That extending an array or list is time-consuming task, right? You have to increase. You have to have a certain larger amount of memory. Also, you have to copy every element in the existing list to the new list. So that's also extra operations that you're involving, right? So something that you wanted to avoid. 그냥 카세트를 틀어놓을까? 그냥 카세트를 틀어놓는 게 아니라. I heard one story about high school teacher. He recorded his voice when the new students came in to class with his tape player and put it on. He sits at the back and play for entire year. I think that's a smart approach. And he even predict when students were laughing, and so it's exactly matched. 그 뉴스에 나온 거 작년 뉴스에 나온 거 못 봤어요? 어떤 고등학교 선생님인데 오래 하셔가지고 다 녹음을 해놓은 거야. 첫 시간에 새 학기 시작하면 첫 시간에 딱 들어와서 카세트 플레이어 여기다 딱 넣고 자기 신문 들고 뒤에 가서 앉는데요. 그러니까 딱 트는데 학생들이 어리둥절하잖아. 막 이렇게 앞에 봐 이런데요. 카세트가 처음부터. 그래서 학생들이 웃는 포인트 그런 농담까지 다 녹음했는데 정확하게 맞아 들어간대요. 1년 내내 그렇게 수업을 하신다고 합니다. 참으로 현명하신 선생님이신 것 같은데. 요따구로 반응하면 그거나 카세트나 나나 별 반응 똑같아요. 그죠? Hopefully, yeah, maybe I will think about that. I will try to consider that as another option, maybe for next year. Okay, so hash table issues. The choice of hash functions. What functions that you use is crucial part of your hash table design. If your hash function maybe generate too many collisions, is that a good hash function? Probably not. Hope you when you build or when you're using the hash functions, you're hoping for minimal collision happenings. So everything is evenly distributed. But that's not always the case in real life. So but still, choice of which hash function to use is another big issue when you're using hash tables. Overflow handling. No hash function is perfect. So you have to prepare for if collision happens, okay. If buffer overflow happens, what can you do? So you have to build a safety mechanism. Even if your hash function seems to be perfect, just in case. The size and number of buckets of the hash table. How big you want? Yeah. 아까 얘기했지. Collision is hash function gives you same value. 키가 다른데 it's two different keys, same value. That's a collision. But overflow is there's no spot to store. So there is some cases that collision happens, but that same spot can hold multiple elements. Then collision happens, no overflow. But if there's only one spot, like the example that we saw here, there's no here when a bucket can hold only one pair, collision happens, overflow happens. 네, 아까 잠깐 몇 번 얘기했었는데 어떤 경우에는 여기 이렇게 뭐 나중에 뒤에 나오는데 솔루션 2개, 3개 붙일 수 있는 경우도 있어요. 같은 쪽에. 그럴 경우에는 컬리전은 생겼는데 오버플로우는 아직 아닐 수 있으니까 뭐 2개 들어왔는데 내가 3개까지는 할 수 있는 경우는 그렇죠. 그런 것 때문에 이제 이렇게 써놓은 거예요. When a bucket can hold only one instances, only one pair, then collision and overflow happening at the same time. So there's a slight differences. Okay, so the size of the hash table. In some cases, when you're actually using this type of stuff in your programs, you're always tempted to bring your hash table size really, really big, like huge hash table. I mean, so you can avoid any possible troubles that you don't expect to happen. So it's important to not to have too much memories, not to consume too much memories, and still wanted to have a reasonable size of hash table. So getting the bucket value of B is also another issue of doing it. So those are the 3 issues when you're using the hash table. It may not ring a bell to you now, but when you actually try to implement this, these things probably the first thing that you should be consider. Okay, hash functions, 2 parts. Convert key into an integer in case the key is not. So here's somewhat tricky part. So keys that we have seen in the examples, some of them are integers, but some of them are not integer. Like those examples from the Python website, there was a name and phone number, right? But because we are dealing with the list, hopefully the where you pointing to wish to be an integer value, 0 to not negative ones. So there is a way to convert those characters into a integer values. Hopefully unique integer values later. If you think about it, character is what? how many bytes in the character? It will come up. Let's see. Assume that character is 2 bytes. So 1 byte is how many bits? 8 bits, right? So even it's a character, it's a 0, 1, 0, 1, 0 1 representation, right? 16 bits. So you shift, they call it as a shift or shift operation by 16-bit. You 0, 1, 0, 1, you just simply convert that as like an integer. Treat them like an integer instead of character. Then you might have some funny values representing those characters. And those values may be unique values, so we can use them as a hash function keys. So we will have the example next slide. Converting key into an integer in case the key is not. Map an integer into a home bucket. Fk is an integer in the range of 0 to b minus 1. Why? Because b referring to a total bucket size, total size of the list, b minus 1, of course, right? So fk, the output of the hash function, always give the value between this range. If my hash function gives a value outside of that range, what does that mean? 어떻게 되는 거야? Zero to b minus 1. Output of fk, hopefully within this boundary, but some key gives here or here. But there's nothing here, no space at all. Probably, most likely, you will encounter some type of errors, segmentation fault in case of C. So because you're pointing to a nowhere. If your hash function is doing this, your hash function is not right. They're not operating correctly. So you should think about to change or fix your hash functions. So that's what it says. Map an integer to a home bucket. F should be the range of 0 to b minus 1, where b is number of buckets in the table. Number of buckets in the list. That's a 2-part within the hash function. That's what hash function is doing. Well, the previous example that we saw is key also integer. Only thing we did was just modular by the number of size of the buckets, right? But this case, assuming key is not an integer, and hopefully we somehow convert that number into within this range. So that's a function they suggest as a typical cases. It's one of the ways to make a unique integer out of a character. So let's assume that each character is 2 bytes long. It is 2 bytes long. Let us assume that integer is 4 bytes long. Integer is 4 bytes. A 2-character string S is a 2-character string S, may convert it into a unique 4-byte integer using following code. So the key is given, but what does that mean? Put a bracket, and they say integer. What is that called? Yeah, casting. Casting, easy way of saying that's an integer, but I'm gonna treat them as an integer from this point on. So if you actually print those out, then you will have some crazy values. So maybe very large values, because it's not accurate of way saying it, but it's like string is 0101. I'm gonna convert that 0101 into an integer. How do you convert the binary numbers to integer? 뭐 뻔하잖아. 2, 1, 2에 몇 승이었고 그냥 무작정 해버리는 거예요. Then I will have some arbitrary integer values. Right? That's what it means to be a casting a force to this. I'm gonna treat this point as this string as an integer from this point on. And then the answer, I need to convert that into a 4-byte string. So this is something called shift operation. We're shifting by 16 bits. Shifting by 16 bits. I put it here. You can skip this part. It's okay not to understand this at this point. So there is a bit of explanation in the textbook, but it's not that much. And plus, I'm not gonna go over it in depth. But this is one of the ways of converting that, converting 2 character into a unique 4 bytes integers. So this is shifting operation, and they do something funny after that. They add them all. 이거 why this is guaranteed unique integer? It's beyond this textbook. Okay? 근데 저렇게 애들 많이 해요. 인터넷에 다운 받아 보면 shifting 그 비트를 이렇게 shifting 한다고 해서 비트를 한쪽으로 다 옮기고 뭐 한 비트로 옮기고 16비트로 옮겨버리고 막 이러면 숫자가 막 바뀌어버려. 어떻게 보면 되게 저게 하는 게 뭐라고 표현하면 되냐면 랜덤 넘버를 제너레이트 하는 것 같은데 유니크 랜덤 넘버를 제너레이트 하는 거예요. 어떤 패턴을 주면 맨날 다른 게 나오게 하는 방법 중에 하나예요. It's okay. I don't expect you guys to understand this for sure. But funny thing is, I also try to use some of the hash functions out there. I don't understand what they're doing, but somehow they prove it's guaranteed to give you unique numbers. If you try to use the same function for 3 characters key, then this code doesn't guarantee the uniqueness of the key, uniqueness of the output of the hash keys. 여기 써놨듯이 이거는 어디까지나 2개, A, B, B, A 뭐 이런 식으로 하는 2개에 대한 키 값을 넣었을 때 되게 뭐 요 안에 들어가는 값이 나오게 하는 펑션일 뿐이고, 예를 들어 요 해시 펑션에다가 3개짜리를 갖다 넣으면 안 될 거라고 얘기하는 거예요. 그럴 수밖에 없지. 3개짜리를 갖다 넣으면 앞에 2자리만 보니까 integer s0 and integer s1 하면 if my key is 이렇게 보는데, 예를 들어 내 키가 이런 말이야. 맨날 이 2개만 보고 새로운 해시 키를 만들어내는데, 예를 들어 A, B, D라는 키가 들어오면 어떻게 되겠어요? 똑같죠? A랑 B만 가지고 하니까, 그죠? 그래서 이거는 2개만 가지고 하는 거예요. 그래서 3개 가지고 하려면 이제 또 아래에 몇 줄이 더 들어가겠죠? 3개 가지고 하는 건 또 다른 방법이 좀 필요할 거예요. So this, if you understand this much, it's okay. That's totally fine at this level. So if you're interested, please try to read example 10.8. I try to look at it, but it's not much. If you're interested in this shift operators, type on the Google. Type on the Google as a shift operator in C. Then they will try to go to step by step on how to shift the bits into different formats. 나도 옛날에 처음 쓸 때는 뭔지 모르고 썼어. 그냥 된다 하길래. 나중에 계산해 보니까 되긴 하더라고. So this is a bit more common than modular, I guess. No, modular is much more common. This is a bit more practical manner of doing it. So mapping into a home bucket, most common methods is by division, modular. Home bucket, K, home bucket equals to K modular divisor. Divisor equals to the number of home buckets. This is modular approaches that we have looked at so far. Hash function is much more common of doing it. So 0 home bucket divisor by B. Yeah. So hopefully home bucket is range between 0 and B. Okay, that's what it says. 네. 아니. 그 어떤 키가 들어갔을 때 나오는 값이 홈 버켓. 어? 그냥 버켓은 이렇게 부르는 거예요. 홈 버켓. 그러니까 여기서 얘기하는 책에서 얘기하는 홈 버켓은 내가 어떤 K 값을 줬을 때 딱 나오는 거를 홈 버켓이라고 얘기하고 그 옆에 있는 거는 그냥 버켓 뭐 이렇게 얘기하더라고요. 네. 그래서 뭐 새로운 그 맞는 키에 따라서 나오는 건 다 홈 버켓이지 뭐. 다 홈 버켓이고. 그 약간 나도 보면서 좀 헷갈릴 수 있겠다라는 생각을 좀 하게 됐어요. The home bucket just simply referring to the if the given K location that I found, they call it as a home bucket. The buckets next to it you can call it a bucket, next bucket, previous bucket. Doesn't really matter. That's more of our textbook way of representation, home bucket, the target that you found. That's why they say home buckets should be staying within this range. That's it. So finally, how we solve this overflow situation, overflow handling. We need more spot to store. What can you do? What can you do? Actually, they're mentioning of two solutions with very easy, somewhat very easy solutions. Search hash tables in some systematic fashion for a bucket that is not full. So I give the certain hash function, hash key. I found my home bucket. Let's say home bucket is here. But I noticed that this is already filled. So they simply say, try to find a systematic way of finding empty spots. If this is empty, this is my home bucket, some function referring to here. So they say, we need to find some way to find a empty buckets in the list. What can you do? Just looking at this. It seems the others are all empty. Yeah? What might be the easiest way of doing this? It looks dumb, but maybe if this is empty, maybe I go to the next one to see if this is empty or not. And then I put the new one into here. Done. Done. Dumb way, but simple enough. Simple enough. That's what linear probing is. Linear open addressing, linear probing is. Quadratic probing, random probing. I don't think textbook mentioned all of this, but let me guess, what might be the random probing? Random, yeah. Just pick any number to see whether they're empty. Go. But better be some type of a patterns in that random. Otherwise, we will have a trouble finding the next, which we will have a finding when we do a searching. If you put a random stuff in here, how do you find it? Even if you have a key, right? So those things you should be careful of. So quadratic probing, I forgot what it is, but I'm guessing maybe jumping every two, maybe more. Some similar to that until you found one. Eliminate overflow by permitting each bucket to keep list of 4 pairs for which it is a home bucket. It's difficult. Eliminate the overflow by permitting each bucket to keep a list of all pairs for which it is a home bucket. Array, linear lists, or chain, or n chain. Or within the same stuff, you try to find the empty spot, whatever the ways that you can find. Or maybe we can keep this one as a single array and put it in. We can put multiple pairs in the same location by putting array, or simply put as something like this. Something like this. If you don't limit the how many that you can have, then will you ever have overflow problems? No, right? But that's not always the case. But in theory, it seems to be if I can add infinite number of stuff in the same location, that I don't have a overflow problem. But if you're using a hash table, and look at your hash table back, if one of your entries is like this, then you're not doing something, you're not doing right. There must be some kind of problem with your hash keys, hash function, because every single time it seems to be pointing the same one. I also made the same mistake when I was doing this too. I think my hash function was perfect. I thought it was evenly distributed, and I do a double check on how my stuff is stored in my hash table. So I just go in one by one and see how many elements are in each one. One case, I had all the elements in the one bucket because I made a mistake in my hash function. Hash function always returning the same value. Doesn't matter what key that I give. Typical mistake that you can make. If you try to build your own hash functions, those are most likely. So I recommend to use hash functions that you can find on the internet, or proven hash functions. Some hash functions are mathematically proved that they will give a unique, they will guarantee the uniqueness in maybe in many different combinations. Okay, that's the basic idea. You basically finished pretty much all the slides, but let's take a look at one by one for examples. Linear open hashing. Hashing with the linear open addressing. Linear open addressing. If a collision occurs, insert an entry into next available bucket regarding the table as a circular. I draw that way. I don't know which way is more comfortable for you guys, but I'm gonna draw. I'll draw the same way as. Same thing. Let's see. Example, the size of hash table is B is 11. Assume this is 11, I don't care. B, I don't want to draw more. 11. Fk is, that's my hash function, Fk, K, B. After inserting the three keys, 80, 40, 65. Okay. 11 modular 11 of 80 is 3, 7, well, 7, 65. 65 뭐냐? 55, 10. I need a calculator to do this. This is fine. Everything is empty. Every location, every home bucket that I found is empty, so I can simply just store those in. After inserting two keys, 58 and 24. So, oh, sorry. Maybe I should write it 80. 아, 헷갈려. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 에이씨. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 10, 80, 40, well, 65. I'm gonna add 58. 58, well, what is it? 3야? 아, 그렇구나. I thought it's 7. 3, 80 is already here. What should I do? 54 should be here. But we'll try to use linear open hashing. Okay, let's move one by right. Is this spot empty? Yes, it does. 54, done. 24, 뭐야? 24는 뭐야? 너는 어떻게 이렇게 계산이 빠르냐? 안 되는데. 24, no problems. What if there's a case, another case that another number may be in looking for same spot? What do? Yeah, you move until you find the empty ones. Give me any number that has a 2. 몰라. 32? 33? 33? Yeah. 모르겠다. 뭐냐? 2 들어가는 거. 맞아? 아, 그렇구나. Let's say 35, then 35. Then you move by 3. It is a hash. It is a hash. Hash with the avoiding buffer flow by maximizing memory efficiency as well. Still hash. It's still hash. It's one of the techniques that can be applied in the hash tables. But I know where you're going to. But then what if you try to search for this number later, right? Search function, that comes next anyways. 아직 hash이야. We're still discussing in hash. After inserting key 35, yeah, 35. Oh, 35. 아, 이거였구나. 35. Like that. Okay. It seems everything is disorientated from here. Yeah. 어디? 여기. 네. Circular way. Circular way. They treat it like a circular linked list. Okay. They probably said it so in table as a circular. Table as a circular. 가장 좋은 건 그냥 여기 보면 그냥 이렇게 하나 더 붙이면 좋겠는데 we're still in the array part. So, okay, 35 that. So you get the idea. What about searching then? This seems to be a bit disorientated. What do you do then? Next time you try to look for 35, whether you have where's the location for 35. Okay, I do the same. 35, 11, 2. 2, but it's not 35, right? What do you do then? It's the same way as for inserting. You move until you see 35. So in worst cases, may not be expected as a constant, but it's still the constant anyways. So search operation, let's see. When you apply this linear open hashing approach to avoid buffer overflow, search operation, then search begins at the home bucket for FK at the key. Home bucket for 35 is here. Continue search by examining successive buckets in the table until you want to. 아, 이거는 다 미안. 아, 이거 설명해 놓은 거다. 미안. This is the way of finding the empty spots. Sorry. You continue the search by examining successive blocks in the table until one of the following condition happens. Let's go back to 35. 35, try to insert a bucket containing elements with key. 미쳤구나. The first one is right. This is search operation. Search one. Sorry, my mistake. This is when I have this hash table like this, and I try to find the key 35. So 35, obviously I'm doing this bucket containing element, the key is not reached until I find the 35 or empty bucket is reached. That means there hasn't been no 35. If there was a 35, there should be no empty bucket in here. Or you go through the entire list again, you're going back to the home bucket again. It means that there's no 35, right? So that's the three conditions that they're actually looking for when they try to find the key value, key 35 in this case, in the linear open hashing. I'm sorry for the confusion. 나도 순간 착각했어. Sorry for the confusion. 맞죠? In Korean briefly, 내가 이렇게 다 해놓고 now I'm looking for search 35. I'd like to find out whether this hash table has a value of 35. 35, I know where to start because this home bucket is 2. 2, 24, no. 80, no. 54, no. 35, yes, then return. There is 35 in here. If there was no 35, 24, 80, 54, but home this is empty one. That it means there hasn't been no 35. So say there's no 35 in the list. If this was occupied with the other values, then I probably go back. There, no, not 35, not 35, not 35, not 35, not 35. When you hit the end, go back, not 35, not 35. But I'm back to the home bucket where I started without any 35. So that says there's no 35 in the list. So if you apply this linear hashing approach in this hash table, this is search function that you can practice on it. So in case of C2 and C3, the table contains no elements of the key K. No key K. Sorry for the confusion. 난 아직도 애드하는 거 한다고 생각했어. 이거 search야, search. Have I ever do this linear open addressing? 난 한 번도 안 해본 것 같아. I never done this. I usually do this, just in case. Yeah. This is when you try to do the delete operation on the hash table that follow this linear open addressing approaches. Delete operation performs a search operation to find the bucket for key K. Clear the buckets, then do either one of the following. Move 0 or one more elements to fill the empty buckets. Introduce the never used field in each bucket. Okay. Just read it. It's not for us yet. Okay, it's okay. So what we're interested in, if we do that, can we still guarantee the good time complexity that what the hash table is supposed to do? Performance of the linear probing, the worst case in inserting deleting time is n, when n is number of pairs in the table. When does this worst case happen? When all n keys have the same home buckets. In worst case, you might looking at n times. You might have to go through everything in this linear probing approaches. But when is such cases that every element I'm adding in always pointing to one place? Then every time the second one will be here, so third one will be here, fourth one will be here. You have to go through everything, right? You're shifting by one. So that's the case for worst cases. If so, you're not building a hash table. You're not doing right. 그죠? 같은 키 계속 나오니까, like the example that I give you. So then you should consider changing your hash functions. It's something that's not right. I build my hash table because my hash function is stupid. I have order of n time complexity. Then why are you using hash keys, hash functions? 할 필요 없죠. 만약에 저렇게 돼 있으면 그냥 리스트 써서 하면 똑같이 order n인데. For the worst cases, performance of hash table and linear list are same, like I say. There's no point of using hash table if your hash function always pointing to a same spot, same buckets, home buckets. However, the average performance of hashing is much better, assuming that you're using a reasonable hash functions. 일반적으로는 당연히 해시 테이블 쓰는 게 훨씬 더 search operation 좋아요. 물론 뭐 우리가 지금 버퍼 오버플로우를 피하기 위해서 여러 가지 방법을 설명해 놔도 저렇게 막 바보 같은 케이스가 있지 않은 이상은 일반 in average it's better than simple list. 처음에 시작할 땐 그렇게 볼 수도 있죠. 해시 테이블을 딱 이렇게 잡아놓고 시작을 해야 되니까. 요 다음에 나오는데 그래서 해시 테이블을 얼마만큼 버켓을 얼마만큼 잡아놓고 하는 그거에 대한 숫자를 얼마만큼 놓고 시작하는 게 좋으냐 그런 것도 약간 나와요. 근데 뭐 그렇게 보면 그렇게 될 수도 있죠. 리니어 리스트는 처음부터 0이니까 빵이니까 그렇게 볼 수도 있죠. 네. 근데 리니어 리스트는 계속 엘리멘트가 늘어나면 여기서 그래서 에버리지가 나는데 엘리멘트가 많을 때랑 적을 때랑 평균을 내보면 리니어 리스트는 엘리멘트가 많으면 서치 타임이 계속 늘어날 수밖에 없잖아, 그죠? 그런 걸 다 케이스 했을 때는 아무래도 해시 테이블이 전반적으로 낫다라고 얘기하는 거예요. 아이고 뭐가. 나 어저께 10시부터 뻗어서 잤어요. 너무 피곤해갖고 너무 많이 떠들었나 봐. 웃어? 비웃어? 10시부터 뻗어 자서 6시에 일어났어. 내가 보기엔 오늘도 그럴 것 같아요. 중간고사 볼 때가 좋았어. 너무 피곤해. 이게 맨날 이렇게 수업을 하다가 한 주 쉬니까 다시 피곤해. 매주 할 때는 몰랐는데. 니네들은 안 피곤하지? 뻔하지. Expected average performances. Expected average, same thing. Expected. I want my hash table achieve at least this much of performances. That's my expectation. So they introduced a few parameters. Again, just for your references, they introduced few parameters like alpha, SN, UN. Alpha, SN, UN. They also tell you how to compute this SN, UN. And in cases, it's okay. Alpha is something called loading factor. Number of elements divided by total number of buckets. Why do they call it as a loading factor then? 뻔하지. I only have B spots. There is n elements. If there is more elements than buckets, then alpha ratio is more than 100%. But alpha, we try to keep the alpha value between 0 to 1 in terms of ratio, like 0 to 100%. Okay? This gives us a brief indicator on, very short indicator on whether your list can handle all the elements. 대충 알려주는 거예요. SN, average number of buckets examined in successful search. Average numbers buckets examined in successful search. Whether it's a linear open hashing or other ways of doing it. I try to find certain things in the key, like previous examples. Count how many buckets that I had to go through. So most of the cases, maybe just one bucket, home bucket. Hopefully home bucket has the value that I'm looking for. Or if it's not, then I might have to go 1 or quadrate 2 or sometimes random like that. So that tells us in big pictures how many bucket movements do I have to make in successful search. UN, on the other hand, unsuccessful search. If there's no elements that I'm looking for, then in worst case, you have to go through the entire list like this, all n's, right? 그죠? So that's three indicators. Time to insert and delete is governed by UN. Why? Because there is no element that I'm looking for. It's counted as unsuccessful search. So time to insert delete will be on govern means that it will be dominated by UN. 그냥 UN으로 다 이렇게 커버가 될 거죠. UN 값으로 커버가 될 것이다. 얘기하는 거예요. So they give you these three variables and they give you the formulas on how to calculate this SN, UN, and using this alpha values. It's okay. It's expected performances. It's okay. You can just take a look at this formula as a reference. You don't need to know in depth. It's okay. So I'm just referring to the table here. If I put that as alpha values that I can control, right? How many? No, not much, but I can analyze. Let's say I have 50 elements to add, and I set up as my bucket size as 100. Then ratio will be 0.5. Using that value, if there's about half of the total number of size, then I can calculate SN like 1.5, UN 2.5. What does that mean? Again, SN 1.5. So in average cases, if I'm looking for something, then I can just move 1.5 times. So if you round that up, maybe maximum 2 movements done. If it's unsuccessful search, then I may have to move more than this. But you notice that if the alpha value gets, it depends on the alpha values. Alpha value 75%, SN 2.5, UN gets really large, 0.9, 5.5, and 50.5. Notice that more elements in the list, then there are more likely more collisions in the list, right? So you have to move a lot within the list. So this is how much that you have to move in order for successful search, unsuccessful search. So what we can control is probably the alpha value. Within the alpha value, things that we can control is probably the value B, because we don't know how many elements will be coming in most cases. So the question comes back to, what is a good value for B? 이거 어떻게 보면 당연한 얘기죠, 그죠? 생각해 보면 사이즈는 이렇게 딱 정해져 있는데 거기에 한 50%가 차는 엘리먼트가 계속 들어가야 되면 그만큼 50% 남아 있으니까 아무래도 컬리전이 덜 발생할 거고. This basically says how many elements that I can add, 50%, 75%, 90%. Obviously, more elements to handle, more chance for collision happening. If collision happening, more chance for your moving around within the list. So if you have too many, about 190%, then you will spend more time for searching. If in worst case, it's not going to make so much difference from just simple list, right? Overall idea of using hash is we try to achieve a constant time lookups. Right? So this is indicators that you can find out which one is which. That's going back to this. When you design a hash table, you should consider the value of number buckets B. They call it as a divisor as D. What number? What is the total size of the list? Should be very important. Throughout many other experiments which I didn't do, over time many people have done it. It seems the best result can be obtained when D is total number of buckets. D is either prime number. Prime number is what? 소수야? 뭐 어떻게 하지? 1, 3, 7 뭐 이렇게 하는 게 소수인가? 어? 아 1은 아니지. 1은 divisible by 2, 3, 5도 맞네? 아, 프라임 넘버도 잊어버렸네. 5, 7, 11, 13, stuff like that. You know what a prime number is, right? So best result seems to be D is a prime number or has no prime number factors less than 20. It's not my result. It's not my result. It's throughout the many different experiments for over 20, 30, 40 years. It seems to be that's a better choice for. So if you don't know, just pick a prime number. And because in many cases, you don't know how many elements you will be handling, right? So just pick a prime number. That might be a safer choice. Safer choice. The key is, how do we determine D? How do we determine D? Has no prime factor less than 20. 크게 해주죠. 프라임 팩터 인수분해했을 때 프라임 팩터가 20보다 작은 거? 그런 인수분해가 뭐냐? 아니야. Has no prime factors less than 20. 프라임 팩터 20 아래의 걸로 그의 배수로 올라가는 수로 하는 게 좋다라는 거예요. Factors of prime numbers less than 20. 프라임 넘버를 쓰거나 아니면 프라임 넘버 20 아래의 프라임 넘버의 팩터 배수에 올라가는 숫자를 고르거나 둘 중에 하나를 하는 게 좋더라 라고 얘기하는 거예요. 인수분해가 뭐냐 근데 영어로. 근데 이해가 가요? 영어 해석으로는 아 그렇구나 미안. 네 맞습니다. 22 뭐? 소인수가 뭐야 또. 맞아요 저 준영이가 맞아요. 네. 내가 지금 얘기한 거에 반대로가 맞아요. 그죠? 20에 넘어가는 거에 프라임 넘버 팩터로 하라는 거 맞아요. 소수인나 이런 건 잘 뭔지 몰라. 미안해요. 내가 정신이 없다. 팩터의 곱하기 배수 20을 넘어가는 프라임 넘버들의 배수 맞죠? 20을 넘어가는 프라임 넘버들의 배수 그렇게 보시면 됩니다. 아, 팩토라이제이션 맞네. 그럼 비슷한 얘기네. 네, 비슷한 얘기네. 팩토라이제이션도 기억이 안 난다 뭔지. 야 오늘 카메라를 찍는데 이렇게 실수가 많아서 어떡하냐. 지워달라 그래야 되겠다. 뭐 어차피 니네들도 안 보고 세상에 어느 사람들도 안 볼 거라 예상을 하기 때문에 상관없습니다만 안 되면 내가 유튜브 웹사이트를 해킹해서라도 비디오를 내려놓는 강수를 둘 테니까. So do take a look at the example in 10, 12 and see the next slide explaining about the another ways of determining D. I mean they also give you some recommendations when you're choosing the D. This is another ways of doing it. Method 1, first determine what constitute the acceptable performances. Use the formula UN as sen. Determine the largest alpha can be used. Largest alpha can be used. Probably not 1. 1 is too much. Less than 1. From the value of n, the compute the value of alpha. Obtain the smallest permissible value of b. So it's in this case assuming that we know the n how many elements will be coming. Then try to find the minimum number of B's that achieve acceptable performances. So it's doing a bit of backward. Why do they try to minimize the B as memory space requirement? Hopefully smaller is better. But it's somewhat obscure, vague. I mean, acceptable performances. It's not clear. I mean, it's up to you, I guess. If you're okay with a 80%, like those values, average 5 movements for searching, then if you're okay with it, then you can certainly choose 75% and whatever that you choose to do. So that's a bit of a flexibility they try to give. From the values of n, the computed value of alpha, obtain the smallest permissible value of b. Okay. Method 2, begin with the largest possible for b as determined by max. Begin with the largest possible value of b, determined by max amount of space available. So you declare really, really big b, considering how much memory that you have. Then find the largest d, no longer than this large value that is either prime or no prime factor of smaller than 20. And then maybe from the large value, you try to reduce by satisfying these conditions. So it's another playing around with this stuff. Or if you're tired of doing it, just pick a number and try. Why not? I don't think it's not gonna make too much differences on your level of programming. You're not dealing with the large ones. I wanted to show you this, but don't have time. Okay, hash with the chain is like this. 아니야, 이거 하나 남았어. I just wanted to show you this quickly. Maybe we have time tomorrow, then next week. Some crazy guys. This is what typical programmers, hackers look like. I don't know who they are, but they're home. Anyway, these people are. This is. I also use this slide for a 무슨 코र्스지? 그만 끝나라는 얘기네. Information security, computer security courses that I teach. Some computer security courses that I teach. These two weird-looking guys, they found something wrong with the hash functions that people use most of the time. So they try to explain this hash, how the hash works. This is exactly what our textbook, our slide looked like. And then they also try to explain the time complexity. The thing I wanted to show you this is, 가자. Worst case in real life, 200,000 multi-collisions in 10 bytes of roughly 2 megabytes. I don't know how many that number is. String comparisons in 1 gigabyte. So that's how much it takes to generate the hash key and movements. Not this. Wait. Oh, this is the one of the hash function. The people use this guy. I guess this is very famous guy who come up with this hash function that you can find. I don't know what they do. But it seems to be somewhat similar to the examples that we saw, right? This guy come up with, he names it as this one. This is hash function that used everywhere, mostly open source, Apache web servers and stuff. Thing is, about a year ago, some people found a bug in this code. They do something, they found out they will always introduce the same bucket. And these two people, the weird-looking people, found out this about. They actually attack this code and find the problem with this hash functions. So this is more of a real-life stuff. 그래가지고 한 2년 전에 난리가 났었어요. 1년 반 난리가 났었던 적이 있어요. 전 세계에 있는 웹 서버를 다 바꿔야 되는 크나큰 사태가 한번 발생한 적이 있었어요. 실제로 쓰는 건 이렇게 생겼다고 보여주려고 넣었어요. 나도 뭐 하는지 몰라. 이거 완전 수학이에요. 그래서 나도 잘 몰라. 나중에 가면 막 프로브 해놓고 해놨는데 나도 잘 몰라요. 그래서 이런 게 있다라는 걸 간단하게 보여주려고 했는데 시간이 없네. Okay, so I will continue on the next part of the hashing later. Okay, I'm gonna call out the attendance now.